Hola. Hey, hello. Okay. Whoa. Okay. What? The camera froze? Really? Yeah, it's not good. Can you actually see what I'm doing? I don't think so. It's glitching. Why is it glitching so much? Properties. Use buffering. Okay, I guess this is better. What? It stops again. Okay, I guess it's good. Okay, so we have to lately it's kind of me, so lately
Of course, it's the best.
to order lately I'm trying to central limit theorem. Is it working fine? It's lagging. Nice setup, thanks, Biniar. I'm trying to make it so that it syncs and doesn't cause bad stuff. Alright, so we will learn, I think it should be here. Then, like that, so that I can speak. Can you hear me clearly, everyone? Hello? Okay, I guess it's clear enough. So, I'm gonna order some water real quick. Water. Pop out chat. I don't want dark mode. Why it's dark mode? The hell? Where's my chat? Okay, chat. Pop out chat. Okay, so I think I'm good now. Yeah. Okay, so we're gonna study central limit theorem, huh? Central limit theorem. So we're gonna do mathematics.
What is easily one of the most fundamental and
profound concept.
More specifically, the Galton board illustrates one of the most prominent distributions in all of probability, known as the normal distribution, more colloquially known as a bell curve, and also called a Gaussian distribution. There's a very specific function to describe this distribution. Very pretty, we'll get into it later. But right now, I just want to emphasize how the normal distribution is, as the name suggests, very common. It shows up in a lot of seemingly unrelated contexts. If you were to take a large number of people who sit in a similar demographic and plot their heights, those heights tend to follow a normal distribution. If you look at a large swath of very big natural numbers, and you ask how many distinct prime factors does each one of those numbers have, the answers will very closely track with a certain normal distribution. Now our topic for today is one of the crown jewels in all. This is a Galton board. Maybe you've seen one before. It's a popular demonstration of how even when a single event is chaotic and random with an effectively unknowable outcome, it's still possible to make precise statements about a large number of events, namely how the relative proportions for many different outcomes are distributed. More specifically, the Galton board illustrates one of the most prominent distributions in all of probability, known as the normal distribution, more colloquially known as a bell curve, and also called a Gaussian distribution. There's a very specific function to describe this distribution. Very pretty, we'll get into it later. But right now, I just want to emphasize how the normal distribution is, as the name suggests, very common. It shows up in a lot of seemingly unrelated contexts. If you were to take a large number of people who sit in a similar demographic and plot their heights, those heights tend to follow a normal distribution. If you look at a large swath of very big natural numbers, and you ask how many distinct prime factors does each one of those numbers have, the answers will very closely track with a certain normal distribution. Now, our topic for today is one of the crown jewels in all of probability theory. It's one of the key facts that explains why this distribution is as common as it is, known as the central limit theorem. This lesson is meant to go back to the basics, giving you the fundamentals on what the central limit theorem is saying, what normal distributions are, and I want to assume minimal background. We're going to go decently deep into it, but after this, I'd still like to go deeper and explain why the theorem is true, why the function underlying the normal distribution has the very specific form that it does, why that formula has a pi in it, and, most fun, why those last two facts are actually more related than a lot of traditional explanations would suggest. That second lesson is also meant to be the follow-on to the convolutions video that I promised, so there's a lot of interrelated topics here. But right now, back to the fundamentals, I'd like to kick things off with an overly simplified model of the Galton board. In this model, we will assume that each ball falls directly onto a certain central peg, and that it has a 50-50 probability of bouncing to the left or to the right. And we'll think of each of those outcomes as either adding one or subtracting one from its position. Once one of those is chosen, we make the highly unrealistic assumption that it happens to land dead on in the middle of the peg adjacent below it, where again, it'll be faced with the same 50-50 choice of bouncing to the left or to the right. For the one I'm showing on screen, there are 5 different rows of pegs, so our little hopping ball makes 5 different random choices between +1 and -1, and we can think of its final position as basically being the sum of all of those different numbers, which in this case happens to be 1, and we might label all of the different buckets with the sum that they represent. As we repeat this, we're looking at different possible sums for those 5 random numbers. And for those of you who are inclined to complain that this is a highly unrealistic model for the true Galton board, let me emphasize the goal right now is not to accurately model physics. The goal is to give a simple example to illustrate the central limit theorem. And for that, idealized though this might be, it actually gives us a really good example. If we let many different balls fall, making yet another unrealistic assumption that they don't influence each other, as if they're all ghosts, then the number of balls that fall into each different bucket gives us some loose sense for how likely each one of those buckets is. In this example, the numbers are simple enough that it's not too hard to explicitly calculate what the probability is for falling into each bucket. If you do want to think that through, you'll find it very reminiscent of Pascal's triangle. But the neat thing about our theorem is how far it goes beyond the simple example. So to start off at least, rather than making explicit calculations, let's just simulate things by running a large number of samples and letting the total number of results in each different outcome give us some sense for what that distribution looks like. As I said, the one on screen has 5 rows, so each sum that we're considering includes only 5 numbers. The basic idea of the central limit theorem is that if you increase the size of that sum, for example, here that would mean increasing the number of rows of pegs for each ball to bounce off, then the distribution that describes where that sum is going to fall looks more and more like a bell curve. Here, it's actually worth taking a moment to write down that general idea. The setup is that we have a random variable, and that's basically shorthand for a random process where each outcome of that process is associated with some number. We'll call that random number x. For example, each bounce off the peg is a random process modeled with 2 outcomes. Those outcomes are associated with the numbers -1 and +1. Another example of a random variable would be rolling a die, where you have 6 different outcomes, each one associated with a number. What we're doing is taking multiple different samples of that variable and adding them all together. On our Galton board, that looks like letting the ball bounce off multiple different pegs on its way down to the bottom. And in the case of a die, you might imagine rolling many different dice and adding up the results. The claim of the central limit theorem is that as you let the size of that sum get bigger and bigger, then the distribution of that sum, how likely it is to fall into different possible values, will look more and more like a bell curve. That's it. That is the general idea. Over the course of this lesson, our job is to make that statement more quantitative. We're going to put some numbers to it, put some formulas to it, show how you can use it to make predictions. For example, here's the kind of question I want you to be able to answer by the end of this video. Suppose you rolled the die 100 times and you added together the results. Could you find a range of values such that you're 95% sure that the sum will fall within that range? Or maybe I should say find the smallest possible range of values such that this is true. The neat thing is, you'll be able to answer this question whether it's a fair die or if it's a weighted die. Now let me say at the top that this theorem has 3 different assumptions that go into it, 3 things that have to be true before the theorem follows. And I'm actually not going to tell you what they are until the very end of the video. Instead, I want you to keep your eye out and see if you can notice and maybe predict what those 3 assumptions are going to be. As a next step, to better illustrate just how general this theorem is, I want to run a couple more simulations for you focused on the dice example. Usually, if you think of rolling a die, you think of the 6 outcomes as being equally probable. But the theorem actually doesn't care about that. We could start with a weighted die, something with a non-trivial distribution across the outcomes, and the core idea still holds. For the simulation, what I'll do is take some distribution, like this one that is skewed towards lower values. I'm going to take 10 distinct samples from that distribution, and then I'll record the sum of that sample on the plot on the bottom. Then I'm going to do this many, many different times, always with a sum of size 10, but keep track of where those sums ended up to give us a sense of the distribution. And in fact, let me rescale the y direction to give us room to run an even larger number of samples. And I'll let it go all the way up to a couple thousand, and as it does, you'll notice that the shape that starts to emerge looks like a bell curve. Maybe if you squint your eyes, you can see it skews a tiny bit to the left, but it's neat that something so symmetric emerged from a starting point that was so asymmetric. To better illustrate what the central limit theorem is all about, let me run 4 of these simulations in parallel, where on the upper left, I'm doing it where we're only adding 2 dice at a time. On the upper right, we're doing it where we're adding 5 dice at a time. The lower left is the one that we just saw, adding 10 dice at a time. And then we'll do another one with a bigger sum, 15 at a time. Notice how on the upper left, when we're just adding 2 dice, the resulting distribution doesn't really look like a bell curve. It looks a lot more reminiscent of the one we started with, skewed towards the left. But as we allow for more and more dice in each sum, the resulting shape that comes up in these distributions looks more and more symmetric. It has the lump in the middle and fade towards the tail's shape of a bell curve. And let me emphasize again, you can start with any different distribution. Here I'll run it again, but where most of the probability is tied up in the numbers 1 and 6, with very low probability for the mid values. Despite completely changing the distribution for an individual roll of the die, it's still the case that a bell curve shape will emerge as we consider the different sums. Illustrating things with a simulation like this is very fun, and it's kind of neat to see order emerge from chaos, but it also feels a little imprecise. Like in this case, when I cut off the simulation at 3,000 samples, even though it kind of looks like a bell curve, the different buckets seem pretty spiky, and you might wonder, is it supposed to look that way, or is that just an artifact of the randomness in the simulation? And if it is, how many samples do we need before we can be sure that what we're looking at is representative of the true distribution? Instead, moving forward, let's get a little more theoretical and show the precise shape that these distributions will take on in the long run. The easiest case to make this calculation is if we have a uniform distribution, where each possible face of the die has an equal probability, 1/6. For example, if you then want to know how likely different sums are,
Oh, it's raining.
In this video, we're looking at basic probability. Now, when I say...
Damn. Holy crap.
In this video, we're looking at basic probability.
Now, when I say basic, I mean probability as it relates to categorical variables, like yes-no type variables. Numerical variables have their own thing going on, and I'll deal with that in later videos. But we're going to be learning through the use of an example here, and here it is. The HBO cable network took a survey of 500 subscribers to determine people's favourite show. Now in this case, let's say there were two categorical variables, one which is gender, male, female, and the other people's favourite show. So I've got Game of Thrones in there, Westworld, and I've just combined all the others into this other category. I'm thinking that those two are probably the biggest shows on the HBO roster. So let's see how this distribution pans out. Now out of 500 subscribers, 80 of them are male that like Game of Thrones, 120 of them are female that like Game of Thrones, etc., etc. And each of these squares we can call joint events. They're called joint events because they depend on classes from two different variables. Now, the other thing to note is that, of course, they're all going to add up to this total figure in the bottom right. But we can also calculate this total column and total row, where we just sum up the total number of people that thought Game of Thrones was their favourite show, and that's 200. The total number of people that thought Westworld was their favourite show, and that's 125. And we can also total up the males and females. It's 230 males and 270 females. But this is not quite a probability distribution just yet. So let's see how we get there. Here's that distribution again. And if we divide everything by 500, which is the total number of observations, we get something which is called a probability distribution. So where before we had 120 females who preferred Game of Thrones, we now have 0.24 in that cell, because that tells us that 0.24, or 24% of the distribution, is defined by that joint event. So that's why we call that a joint probability. So that 0.24 is called a joint probability. And the way we can write that is to say the probability of female, the event where the person is female, and the event where the person likes Game of Thrones, is 0.24. Now you might see it written with the word "and" in between, or else you might see it with this sort of upside down U, which we're going to call intersection. So that's just a fancy statistical term to say the intersection of female and Game of Thrones, which is of course that joint probability. Now collectively, those 6 cells here form what's called the joint probability distribution. So all of these 6 cells are going to add up to 1, because if you think about it, everyone in this distribution has to be in one of these cells. You have to either be male or female, and you have to have selected one of these options. So it's no surprise that this should sum up to 1. Now we can also calculate what's called the marginal probability, called as such because it's in the margins. Another term for this is the simple probability. So just be aware of that if you see the phrase simple probability. But here this 0.4 refers to the raw probability of someone liking Game of Thrones. And I'm sure you can tell it's just the sum of both the male and female joint probabilities. Now, of course, this actual column here is called the marginal probability distribution. So just like we had a joint probability distribution, this one I've highlighted here also sums to 1. Now, the thing to appreciate is that this marginal probability distribution completely ignores gender. It's as if that variable doesn't exist here. But be aware also there's another marginal probability distribution down here. And in this case, it would ignore the show of preference. But again, the subscriber being male is pure as well.
Okay, makes sense. Just to computer network, right? damn, the battery is low. That's no good. Whoa. This is heating up real bad. Yeah, it's heating up real bad. Heater. Which you can normally interconnect.
Maximum 124 host computers normally in one Ethernet. Okay? Yeah. Ethernet means what is Ethernet? It's a traditional technology to connect devices in the form of local area network or wide area network. It has supported. What's the node? Node means computers or a switch or a router, whatever node can be a node. Okay, but how to connect two nodes to form a network? That's the question. And here we have cloud computing. Cloud. What is a cloud? Cloud means network. Many computers connected with a router, switch, and they can exchange messages. That idea is called a cloud. So yeah, I will make the questions based on the slides. The whole course is based on a network. Because we cannot imagine and talk about like this now. Yeah, we are talking about logical channel. What is logical channel? What's the node? Node means computers or a switch or a router, whatever node can be a node. Okay? But how to connect two nodes to form a network? That's the question. And here we have cloud computing. Cloud. What is a cloud? Cloud means network. Many computers connected with a router, switch, and they can exchange messages. That idea is called a cloud. So the cloud is just abstraction of a huge network. We use the word cloud. Cloud means easy word, easy. You say, I'm using cloud for computation. Easy. But actually, it's very complex. Okay? So a complex word cloud is just abstraction of a complex network. Okay? Yeah. So here the problem is how to connect computers to make a network. So we are using the word link. Link means connection. And in the previous class, we have seen many models. Hey, this is the updated slide you can download from the MS Data. What's the node? Link means connection. And in the previous class, we have seen many models. Hey, this is the updated slide you can download from the MS Data. Okay? The old lecture 2 slide was not updated, I changed now. So we need this information. Network are based on a pattern or a principle. That is called OSI model. It's a 7-layer model. from here, physical layer, data link layer, network layer, transport layer, section layer, presentation layer, application layer. We have seen in the previous class. Okay, this is the basic model of a network. But the whole network, different network, they don't have this model. But especially internet. Internet, what happens is it will never follow the 7 layer. Out of 7 layers, it will follow only 5 layers. So internet use physical layer same. Okay, physical layer same, and the data link layer same, but network layer same, or transport layer same, but presentation and the section and the application combined with same application layer. Okay, in internet. So internet follows this. Okay, but this is a standard network, LAN, WAN network. But internet nowadays all the networks are internet, so it will follow this. Here, what is the difference? The 3 last layers, section, presentation, application, combined into 1 layer. Okay? Yeah. So there is something there. So you can see internet model. Then, what is the group of layers in application layer? This together, you can say internet layer, and this is a hardware layer. Because hardware is here, hardware is here. This together, hardware layer. This is the IP, internet protocol layer, internet protocol, and this is. So example, what is the application example? Of course, Google Chrome, web page, Mozilla, Firefox, whatever application. Okay. Yeah. Then what is the example here? Transport and network layer supported by transport control protocol, internet protocol, software. And here, what is the example of this hardware part? Ethernet port connection, cables, software drivers, network card drivers. Okay, drivers. Okay, now. Yeah. So this is the summarized form of our network layers. Okay. Yeah. And also you can see something the layers here. This is the 5 layer 1, 2, 3, 4, 5 internet. Okay. Sending sender sending. And receiving computer, and this is the network connection between, and here PDU, what is PDU? Protocol data unit. So we can see what is here. Application layer, mostly it use HTTP transfer protocol if you use web page, send request.
Whether we want to construct ultra trivial to network with one link, connect the 1 billion host, but we need to understand the
Send request to get the server. Suppose Amazon.com, any.com, it should send the request and send it from the server, you get it back. So how it flow? So these 5 layers, how does it work? So application layer, you request for a website program use HTTP protocol. Then what happens? The transport can convert your request into TCP format, TCP frame format inside your HTTP and request. The network layer convert into IP. What is IP? Internet protocol. But inside this IP framework, the TCP, HTTP, and request is there. Then what happens? Data link layer convert into local area network transition form. It will make its own packet framework inside IP, TCP, HTTP request. Then physical layer, you cannot say anything because it's data, binary data. Everything in the form of binary transmission. Actually, this binary data transmit in the form of electromagnetic radiation because electromagnetic radiation protect the data from
electromagnetic.
coverage. Okay, and said it can pass through any conduit or any any layers. So this is the way you are requesting your website. Then you can see this is the network. Network behavior packet. This is the packet form, segment, packet, frame. Finally, this is the frame. Okay. Then the bit, the receiving computer. So this is the receiving computer. Okay. Receiving computer receive the same data, and what happened? It will open the packet. Okay. Open the packet. Finally, it will receive the request. You understand? Then this is a server. It understood what this computer wants. This is the Amazon server or Google server, and then it will reply back, same back to get the web page. Okay? Yeah. This is the way all the protocol layers support. I mean the network layers for internet. Okay? Internet. Okay? Yeah. So here IP is the internet protocol, HTTP is the hypertext transfer protocol, TCP is the transmission control protocol. All protocols are based on the internet. So internet is based on the protocol. Okay. So this is a transmission computer, sending computer, receiving computer. Okay. How the layers support. You understand? Okay. So now in this topic we are going to see physical layer. How to transmit the data, binary data, from one computer to another computer through the network. So problem, connecting to a network, you see, these two pictures are taken from, not from our different networks, okay? Yeah, because our network is not from this one, so this will make it more easy to understand. So now we continue chapter 2, problem connecting to a network. How to create a network by connecting the link. Whether to construct a true node network with one link or connect multiple hosts to an existing network, we need to address the following issues. In order to make a network with link means connection, cable connection, you need to understand the following issues. First issue is we need some physical medium to make the connection. So we need some physical medium. So here we can imagine Wi-Fi is also a physical medium. Why? Because it uses air. Okay, air. Anyway, we need a physical medium to connect computers to make a network. So the physical medium may be length of wire, cable, or optical fiber, or tangible medium such as air. What is air? It uses Wi-Fi signal, Wi-Fi, air. Through which the cable connection or physical medium may be cables, length of wire, cable connection, or fiber optic, or a air, through which data bits are transmitted via electromagnetic radiation. So data bits are transmitted via electromagnetic radiation. That means the physical layer collects the signal from here and transmit in the form of electromagnetic radiation, and we remove the electromagnetic radiation and get the pure data and send to the receiver. Okay? So why electromagnetic radiation? If there is no electromagnetic radiation, that means we cannot access Wi-Fi. Why? Electromagnetic radiation can allow the data to pass through all the medium like 1 way or all everywhere. Okay? So finally, the data transmit to electron.
Whether we want to construct a trivial two-node network with one link or connect to the 1 billionth host to existing network like the internet, we need to address a common set of issues. First, we need some physical medium over which to make connection. The medium may be a length of wire, a piece of optic fiber, or some less tangible medium such as air, through which electromagnetic field such as, for example, radio wave can be transmitted. It may cover small area, for example, office building, or wide area like transcontinental.
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 Waves, either through cable or the air. What is air? Wi-Fi or optical fiber. So that means it may cover a small area or office or wide area. We don't know. It depends on the network. Okay. So this is the electromagnetic waveform. To understand, it is taken from a website. So you can see the blue color is a magnetic wave. And the red color is electron. So all combined together electromagnetic wave. Okay, that's right. Electromagnetic waves form a radiation that travels through the universe. They are formed when electric field and arrows couples with magnetic field through arrows. Okay. So electro and magnetic. This is the direction of the wave form, but they have both field. Magnetic field, electric field. Magnetic field, electric field. So this is the form of the wave transmit. Okay. Yeah. So the wavelength is 2 pi part is a wavelength, or this 2 part is a wavelength, or this 2 part is a wavelength. Anyway, this is the real transmission information. If you just information, you may think what is an electromagnetic wave. Electromagnetic wave is a signal has both electric and magnetic takes field, electric and magnetic field. Okay. So what the transmission use electromagnetic wave in Wi-Fi or everywhere. What is data is converted into electromagnetic wave form. Okay. So next one, we continue problem with the connecting to a network. Connecting 2 nodes with a suitable medium is only the first step. So 5 additional problems must be addressed before nodes are successfully connected to form a network. What is the meaning? To form a network, to exchange data packet. To exchange data packet, you can see the data packet. Packet transition, you see packet created here from the user and the packet converted to segment and then back.
Connecting 2 nodes with a suitable medium. What is suitable? A suitable medium is only the first step. However, 5 additional problems must be addressed before the node can successfully exchange packets. And once addressed, we will have provided layer 2 connectivity. Layer 2, which is data link layer. What? Where's my water? Okay. Water.ครับผมสร้างน้ำยังไม่มาครับทุกอย่างครับ Oh, sometimes I got a feeling, yeah. Oh, sometimes I got a feeling, yeah.
Become free. then it becomes byte. Yeah. So the reception same. Okay. So we use the word data packet here. Yeah. So
the first is encoding bits into transmitting bits so that they can be understood by the receiving node. Okay.
First problem here, once we have connected the cables to transmit data, how to transmit? We know that data transmit in the form of packet. So as per layer 2, terminology of OSI architecture, layer 2, what is layer 2? Yeah, layer 2 terminology, yeah. Layer 2, this is the data layer 2, data link layer, okay, data link layer, take here, hardware part, it is the cable connection, and software drivers, okay, anyway, we just check it here. So data transmitted in the form of packet. Then, how to transmit data in the form of packet? You can see from the figure, finally, data becomes electromagnetic wave.
The first is encoding bits into
binary signal here, then if the data sent purely through the network is not good. You know why? Data get corrupted. So data must be protected. How to protect? Because data from one computer to another computer transmitting through a huge network, Wi-Fi or cable connection, whatever, there is a problem of missing data. So we have to address, if you are a network guy, network administrator, network designer, you should know how to protect the data, how to make the data strong before transmitting from one computer to another computer. So here the physical layer generate the data for the user request. But how to send it? That's a question. Of course, it is sent through the network medium, physical medium, cable, Wi-Fi, whatever. But there is another problem here. The data packet must be encoded. That means first issue is encoding bits onto transmission medium so that receiving node can understand them. That means the data must be encoded. That means the real data must be converted to different form. What is encode? Encode means data is converted into transmission form. Here, we don't talk about electromagnetic world, we talk about binary data, okay? Data converted into some form, that is called encoded form, okay? The word encoded is important. That means, from the sender, this data is encoded and sent to the receiver. From the receiver, what happens? Receiver must do what happens? Receiver must convert the encoded data into original data. What is called? It is called decoded. Okay? So encoded data sent from sender to receiver, and receiver must decode it to get original data. Okay, understand? Okay? Yeah, let us see encode and decode. So first issue is how to transmit data packet from one computer to another computer. Yes, the issue is first encoding, to encode the data bits before transmitting it into the receiver side, receiver side. Okay? Yeah, receiver side. So data must be encoding. This is the first issue. Second is delineating the sequence of bit transmitted over the link into a complete message that can be delivered to the end node. That means it is the problem of encoding bit. First encode, then transmit the complete encoding data bit to the receiving side through the link without missing any pattern, any originality of the data. They have to transmit correctly. So, how to transmit the encoding bit? First we have a data packet, it must be encoded from the sending side, then encoded data must be transmitted properly. Why? Because the receiver must understand the encoded data. So, we have to convert the encoded data into some form, this is called a frame. So, frame, okay, frame. What is frame? The encoded data packet can be known as frame, okay? and the frame can be identified by the receiver frame. Okay. Anyway, the point here encoded. Okay, encoded. So here, so this is the first encoding bits. Second, delineating the sequence means the change the pattern. See, delineating means change the pattern of the normal data. See, this is the binary data. To change the pattern, delineating. Okay, before sending. Then this delineating issue is a framing problem to make frames. Then third problem, because frames are sometimes corrupted during transmission, also detecting them and taking the appropriate action is necessary. This is the error detection problem. So the third issue is, so first encoding the data, second change the data pattern before the transmission for the delineating the sequence of bit. This is the framing problem. Once the frames are created, then the next issue is any error, then there should be an error detection algorithm must be added with the data because frame may be chance of corruption, missing data. The next issue is how to link up here, reliable, even though it corrupts frame from time to time. Then fourth issue is, even though there is a corruption error in the frame, then how to transmit reliable signal. That means we have an error detection problem, and once error is detected, number 4, solve the error, and make the signal reliable. What is reliable? Everything is clear. You can trust the signal. Then fifth issue is, in that case, multiple hosts share the link. It is necessary to mediate access to it. This is the media access control problem. Then we believe that not one host, there are many computers are connected. They all receive the signal without error. This is the multiple access control problem. That means we are not sending the data from one computer. There are many hosts, many computers. So here there are 5 issues of encoding and how to send the encoding signal in the form of frame. If there is a frame, then there is a corrupted frame, then we need a error detection problem. Once the error is detected, then how to send the errorless signal reliable form. Then if there are multiple hosts, how to deal with that. So these are the five additional problems when you connect, when you link a network to using computers and link connection. Okay. So if you are a network administrator or designer, you should know about this big problems. The goal is to survey the available link level technology to solve these 5 fundamental issues of node connection. So the goal is, if you are a network designer, you are going to create a network, you should know the available link level technology to make link connection. What are the conditions? It must perform encoding, how to transmit encoding bits through the cable, then it is called a frame, then if there is a frame, then there is a chance of corruption, then how to add error detection code, then once the error detection code is added, then how to solve the error and send reliable signal, and next, there are not one customer, one host, there are multiple hosts in the link, then how to deal with multiple hosts. So these are the 5 fundamental issues facing, especially inside of the face, okay? Yeah, network implementation. Okay, now? So, see, I told you the network thing, you see, you get internet on everything easy, but behind complex technology is there. So if you really looking for network, you should know all the details, okay? Yeah. Then technology landscape. At the other end of the network spectrum, a typical user encounters link to connect to a computer to existing internet. In your home, you get internet because you get through AES connection. They connect through your telephone connection, and from the telephone, you connect to Wi-Fi. Let us see what are the connection at home. We can have wireless link, Wi-Fi link, or we have cable connection. It's called a LAN cable connection, or you can have hotspot connection. Hotspot. From the phone, you can send signal, data connection signal to another computer. That's called hotspot. be a fiber optic link, which is provided by Internet Service.
Michael Schofield, structural engineer, 5 years for armed robbery.
Michael Schofield.
Provider. I just mean, for example, you may contact proof service or AS and I forgot the name. Yeah, there are many internet service providers here. You call them, they will connect you. Okay, they use either fiber optic cable or copper cable. Okay, so figure 2 will illustrate various links that might found on a today's internet. Okay, yeah. So you can see this is the internet, global internet. And you can see from the global internet, the router connects to the internet service provider. So internet service provider in a country has many routers, and this is suppose your home. So from the router, it can send to your home machines like a mobile phone or tab or computers. Okay, yeah. So internet service provider, either any company, what they do, they access the rest of the internet by using their own way. Okay, then from that they can deliver to the normal people. Okay, so the cable access you can see either fiber cable, Wi-Fi, cellular. Okay, this cable connection, maybe Wi-Fi. Okay, depends on your home. Mostly home, you have Wi-Fi connection, and also you can have cable connection. So next one, next one, upon the left figure 2.1 shows a variety of end user devices ranging from smartphone to tablet to computers connected by various means to an ISP. So you can see a lot of users here at the side here. We've got a host are getting internet connection by internet service provider. So in your case, you are getting internet because of our internet service provider is AU. Okay? Okay now? AU. Okay. So AU can access to the rest of the internet and it will deliver to the campus or student can get Wi-Fi connection. So while those links might use different technologies, they all look same in this picture as a straight line connecting a device to a router. See, maybe this different link, you see fiber link, is a cable link, Wi-Fi link, all look same. But anyway, they are getting from internet service provider. So internet service provider can provide the network connection through any type of link, either fiber cable or fiber link, copper cable, Wi-Fi, cellular, terminal for. Some links connect the routers together inside the ISP, internet service provider, as well as the link that connects the ISP to the rest of the internet. You can see the internet service provider has a network. Inside there are many router connections, but one of the router from internet service provider from AU, this is AU, then it is connected to the external rest of the internet by using another router. See, this is called a peering point, peer point. So which consists of many other ISPs, most connect. So you can see there are many ISP, many companies are connecting the internet to the rest of the world. It's not shown here. It shows only one internet service provider. Okay. Maybe inside. This is a general internet service provider. One router for the type of one router, another company we don't know. There are many companies combined together. They are making the internet and they can provide internet for you. You mean the host people, host are the end users. Host. Okay. In figure 2.1, the link all look alike. Because a network architecture is to provide a common abstraction of a complex network and links. That means by looking this, you think very easy, you can see this link may be fiber cable, this link, Wi-Fi, this link, something else. See, all look alike. Why they look alike? Because it is an abstraction. This picture is an abstraction. It hides the complex network connection from the user. Okay? Yeah. So the whole link looks same because it's a common abstraction of network connection. The idea is that a lab
thumbs up. A new setup? No, it's just an old setup. Not particularly new. Just I'm here, the webcam is here, and the table cam is here. Yeah, nothing new. Just, you know, the webcam there, the vertical cam. I mean, no, this is the same camera, but it's cropped it, and the table cam it's here to see this one, and then yeah, becoming a girl crying. And then I have one more camera, which is for this camera. So if I add one more scene, this would be so if I add one more scene, then you will get one more camera, which is this camera. So I have three cameras. One is the laptop camera. One is this camera, and one is this camera. It's facing down. This. Is this your dome? Yeah, it's my dome. Yep. This is my dome. And I have a microphone here. Yeah. Pretty neat. Kinda. Just basic stuff. And then if you want to see my setup, it's just like that. Yeah, it's as you see here. So I don't want to. I can use keyboard here. So but the computer is heating up. So I usually put my keyboard right here. If I don't have iPad, I'll have my keyboard here. My phone is here, and then some wire dock cable there and stuff connecting to the monitor. Yeah, this is personal information. That's not good. Yeah. Which pad is that? They give you a TV? This is iPad Air. This is iPad Air. It's just normal TV. I can't even watch it. I don't watch TV, by the way. Yeah.
for a smartphone, does it have air?
Does it have air? Yeah. Bruh, your parents loaded? No, because the thing is here's the thing, okay? Here's the thing. So when I went to the university, as you know, I only have PC. I don't have a laptop, right? I don't have a laptop. So if I go to university, I need a laptop to program, to do programming in class. So I need a laptop. So I brought a laptop I bought a laptop, a Windows laptop, which is called a Gigabyte, a brand called a Gigabyte, and it was working fine for 1 week, and after that it's not it didn't work fine for 1 week. It was working for 4 or 5 days, and then it fucked up. Like it started glitching. It started to do some wacky shit, and then my initial thought was, oh, if I'm gonna buy a laptop, why don't I just buy a decent one, like around like i7, a graphic card like could be 2020, anything 1060, could be anything, right? Doesn't matter, but just I want a quick processor. i7 would be fine, like not the top tier one, like i7, the normal, Gen 6 i7. Now it's like Gen what? i7. Yeah, now it's generation 13. Yeah, like just this would be fine. Like it's not expensive like this. Let's see. Yeah, 6th generation, like yeah, 3,000 baht. 3,000 is like $100 or something. Oh, you can't even see my screen, damn it. Like this one, i7, like this, like like $100 around that. So I was then I brought that. Like it was not that I mean the processor was not that good, but it was okay with programming. I can do most of the thing. I'm not doing like so high-end programming like whatsoever. So I brought that, it doesn't work. So I think like, oh, I like Windows, why don't I change to Mac? I want to experience Mac because I know how to use Windows and I know how to use Mac. So it's like, oh, why don't I buy a Mac? And then when I buy a Mac, I brought it with like I brought it, and then I really, how do I say it? So I brought a Mac because the Windows machine was whack, and then I want to try out Mac OS. So that being said, I brought a Mac. Once I brought a Mac, it was perfect. I can do everything just like Linux, like very similar to Linux. And then when I went to university, I realized that when the teacher was presenting the slides, I need to write down the notes, like, oh, this. So for example, right, so if he's teaching this slide, like this slide, right, this presentation slide, so I need to be able to highlight, be able to write notes like what he said. So I was thinking like, oh, another option is if I get like this one, like a writing tablet, like a pen tablet, and then connect to my MacBook, then I could do it. But the thing is, this doesn't work well, it doesn't smooth, it doesn't have the software, it doesn't have many things, right? So essentially I thought like, oh, why don't I buy like just iPad, so I just brought iPad Air with a student discount. So it was not that expensive. It was not normal price, it was like discount price. So yeah, that's why I have iPad. Which one is it? It's iPad Air, but with student discount because I bought it with my student card. Yeah, and then I really enjoy. I could do many things with this iPad. I could go to school with it. The pen tablet. $100, I think. $100. Oh no, not $100. Like 50. Sorry. Yeah, 40 or 40. Yeah, around 40 to $30. Yeah. But I love it this pen tablet, when I'm at home, I can use it because I'm connected to my monitor and I can, you know, because I'm not so good at, you know, like representing things in my head, so I need to draw it out sometimes. So I find this is very good when I'm like learning a data structure and algorithm. I can draw things and stuff in the thing, and I can also like show you guys like stream if I want to stream. I want to express the idea. Which one is the pen tablet? This one. I think I need to remove the filter. You can't see, right? Yeah, this one. This one. Okay. So if I demonstrate some pen tableting stuff, I think it will work fine for now. Let's see. Okay, the notes. Yep. Well, okay, so if I try to write something, yeah, it works fine. Hello world. Whoa. Yeah. Oh, you can't see the screen. I just wrote it, but it's fine. Okay, let's study.
What link it is connected. The only thing matters is that it has internet connection. See, you don't care how you get internet, okay? The thing is we have network connection, that's all. You don't care. Mostly it is from air, Wi-Fi 4. You don't care, okay? But at least it's time the complex technology from a user. User enjoy internet, but doesn't even know how it's coming to your computer or your phone, okay? Similarly, a router doesn't.
The idea is that the laptop or smartphone doesn't have to care what link is connect to. The only thing matter is it has a link. It has a link to the internet. Doesn't care link only matter. Okay. Similarly, a router doesn't have to care what sort of connection to. No, it doesn't. How do we make all of this link to end user and router look efficient? Okay.
Now you care what sort of link connect into other routers. See, your router doesn't need to care, right? Because all the routers are the protocol, everything is correct. It doesn't care. Whatever signal comes, it will transmit. Okay? Yeah. Because routers are based on the protocol. So routers send data packet to the link, expecting the packet to be delivered. Okay? So the router, internet, from internet, the router send to the ISP, internet service provider. From this router, it will go to next router, depends on the data packet. Okay? And the algorithm. So it doesn't care what type of connection between two routers. Mostly, it may be cable connection or fiber optics or Wi-Fi, we don't know. Okay? So how do we make all this link? What is link? Connection between two routers, link. Okay? Link. How do we make all these links to end users and the routers look sufficiently aligned? So there's a question from the room.
How could I make that? Are you using Cisco packet tracer in class? Not, no, we are not using. It's just heavily theory, but not practical. This course. So. But no practical, yeah. But you like if you like, yeah. There's no practical, but I try to use practical to I try to use theory to do it in practical. So that's why I have some. This is not related to the school. This is just I was playing with it so that I can understand, practically. Yeah, but there's no practical. But in the book, on 1.4, there's like software like this, but they skip this. They did not tell us to do this. But I'm planning to do it. Planning to learn this too. Yeah.
Anyway, the question has answer here, we don't need to worry, okay? That means how this link connection exchange data between the routers, okay? What type of data? One router send data to another router. How it understand? What type of packet? How they send? Similarly, from a router, it will go to the host. How the data packet look like? How they transmit? So this question, we have some answer. How do we make all the link to the users and the routers look same, alike, same? First, deal with all the physical limitations and shortcomings of link in the real world. See, we said the number. What is the link? Connection between two router or connection between a user, host and a router, or connection between rest of the internet and the internet service provider. They are used link. So what type of the link is that? How the links are activating? So here we saying that the link is a physical connection. It has limitation. Typically copper wire. Copper wire is some form such as shielded or unshielded twisted pair cables. See, you never heard about it. So this cable is a copper wire. It has a shielded pair or unshielded pair. We don't have to consider the inside. Okay? And in this cable, for the RF connection, copper cable, but inside we don't know whether it's a twisted or shielded pair. Similarly, all the cables, different cables are used for networking, and different cables here Wi-Fi. So you have same cables here. So here, typically copper wire has different form: shielded copper wire or unshielded. Okay. So please got the point: shielded or unshielded twisted pair cable, mostly for internet and landline phone. So landline phone, internet, Ethernet, they use copper cable, shielded, unshielded, and also they use coaxial cable, optical fiber cable, air, space for wireless cable. So you can see the picture: shielded twisted pair cable picture here. You can see something here. It will prevent electromagnetic radiation leakage. Electromagnetic radiation leakage can be prevented by shield. But unshielded cable, UTP, there is no shield, only cables. But here you can see coaxial cable. Coaxial cable has some sort of shield, okay, shield. And also fiber optic cable has the fiber, it will transmit the light like fiber core, and it has some cladding, plastic covering. Okay, so there are different type of cables used for network connection. It depends on the needs of that network, whether shielded twisted pair, unshielded twisted pair, biaxial cable, or fiber optic cable. Okay, so most of the Ethernet here they use fiber cable because it can support a lot of people simultaneously, high bandwidth. So all the links are made of cables, either shielded twisted pair cable, or unshielded twisted pair cable, or coaxial cable, or fiber optic cable, or wire. So air. What is air? Air for Wi-Fi. Air is a medium. So Wi-Fi. You cannot see air. So all the links are made to propagate electromagnetic signals. So see, you can see here in the picture, this binary data converted in electromagnetic form and sent to the network. So what is electromagnetic waveform? This is the diagrammatic representation of electromagnetic waveform and sent to the all the link transmit electromagnetic radiation. Okay. So all the links are made to propagate electromagnetic signal. Here means electromagnetic signal, such as radio waves. But here we don't talk about that one. We only talk about database. Here we don't talk about electromagnetic radiation. Actually, the network data Wi-Fi what coming in the form of electromagnetic radiation. But we don't care now. We only talk about what database. What is database? Here. Before transmitting the data into electromagnetic radiation, we only talk about this one. 1 0 1 0. Okay? We don't care electromagnetic radiation. You know why? It's complex. Okay? Complex. But believe that all the data transmitted in the form of electromagnetic radiation. That's why you get Wi-Fi, you can see anywhere in the room because electromagnetic radiation can penetrate through the wall, something or roof, no problem. Okay. So secondly, the important link characteristic is the frequency in hertz. You know the frequency. How much speed? Speed means frequency of the signal. So electromagnetic radiation has a frequency mostly 300 hertz to 33,000. Okay, 3,300 hertz. 3,000. So this is the frequency range of electromagnetic radiation using for network. Okay. So you can, this is the cable. Okay. Anyway, frequency. You don't need to memorize this cable. So the point here, all the binary data transmitted in the form of electromagnetic radiation. That's why you can get Wi-Fi. Otherwise, your Wi-Fi is blocked by conflict. But electromagnetic radiation can penetrate through the glass, one big roof, no problem. Okay. So this is the cable flow. You understand? Different cables used for networking. Okay, but right now you don't use any cable because it's Wi-Fi. Okay, so here different type of cable, unshielded resistor pair, mostly for telephone, unshielded resistor pair, category, Ethernet, and a different type of cable. And you can see the fiber optic cable. The speed is 10 GB, 10 billion bits per second. Yeah, and different category of shielded resistor pair cable, 100 GB. Okay, 100 GB. So this is the cable used by network designer to connect computers to make network. Okay, so if a strong network, they have used category 7. Category 7 is a shielded resistor pair. This is a shielded resistor pair cable to connect network from the router, and speed is 100 GB, 100 gigabits per second. Okay, gigabits per second. The cost is very high. Anyway, any question? So anyway, we understood that data transmitted in the form of electromagnetic radiation through the cable or fiber optics or Wi-Fi. Air. Okay, air. And also, one more thing we forgot. Before transmitting electromagnetic radiation, we have to convert, encode the data. Okay, encode the data. Why encoding? It's a protection mechanism. Encode the data. Okay, encode the data. Anyway, we are here. The distance between a pair of adjacent maxima or minima of a verb measured in meters is called wavelength. So if electromagnetic radiation, we know that all the internet signals are transmitted in the form of electromagnetic radiation, and the distance between two high part of the verb is called wavelength. It is measured in meters. Okay, meters. So anyway, let us see the equation. Very good. Don't need to worry. Actually, it's a little bit physics here because I told you the computer network has physics, computer science, hardware, mathematics, everything. Okay, yeah, that's right. distance between a pair of adjacent maximum of a verb is called verb length. So the verb length is important. If you are a network designer, you have to calculate the verb length in order to translate the signals. So what is the verb length? Verb length means the distance between the two height of a verb is called a lambda. So a verb length is velocity divided by frequency. If you know velocity, if you know the frequency of the verb, you can calculate the verb length. Okay? Yeah. Velocity divided, this is the verb length, too high or too this low also, or too high, or verb length. How to get verb length? You have velocity and you have frequency. Of the verb, you can calculate the verb length in meters, okay? Meters. So verb length is important if you are a network designer, you should know the verb length of electromagnetic radiation. If the verb length is small, you cannot calculate the signal properly, so you have to be careful. So there are some machines to check the verb length. You don't need to calculate, you just show the Bluetooth can calculate and show you the result of the verb length. Then if the verb length is not strong, then you have to change some hardware like that. It's the duty of the network engineer people or network designer. Okay. Here we don't go deep in that area, but please note the point, there's a wavelength. Okay? There's a wavelength. Okay or not?
Okay or not? Okay or not? I never have cleaned my keyboard. It's my first time. Go there. Boom. There you go. Keeping it up. Okay. Yay. Why is this happening? Calculating. Let's see. The vacuum copper. Velocity. Power 8. No. And copper. Really?
How to calculate wavelength? Velocity divided by frequency. If you know velocity of the verb, if you know the frequency of the verb, the division will result the wavelength. The unit of wavelength meter. Since all electromagnetic waves travel at the speed of light, depending on the medium, the speed of light divided by the wave's frequency equal to the wavelength. So we can say the speed of light V divided by the frequency of the wave is the wavelength. For example, 300 Hz electromagnetic wave traveling through a copper cable would create a wavelength of 667 multiplied 10 power 3 meters. So how do you get 667 multiply 10 power 3 meters. This is the frequency. What is the velocity? Speed of light in copper is 2.001 multiplied 10 power 8. That means 2. If you have a calculator, you can do that. What is that? The wavelength is equal to frequency.
Right. Yeah.
Sorry, not frequency. What is that? The velocity 2.001 multiplied 10 power 8 divided by frequency of the wave 300 hertz. So it will calculate, you will get 667 multiplied 10 power 3. Okay? Yeah, correct. Because we can remove this 2 0 or 10 power 6. And this will be meters. Okay, now. Okay? So, simple calculation. Then question lambda. What is lambda? Lambda. Okay, lambda is a lambda. See, I use the simple lambda. Lambda is the indication of wavelength. Lambda. Okay. If you have the frequency, you have the velocity, you can calculate the wavelength. Similarly, figure 2.2 from the book shows electromagnetic spectrum. This for the communication. Let us see the electromagnetic spectrum. So this is the frequency starting from 10 hours to the. This frequency for the radio communication. This is the microwave. Those body you can use inside your microwave. And this is the infrared radiation, ultraviolet, X-ray, and gamma. But the satellite communication use this range satellite communication. This is the fiber optic communication frequency 10 power 14 to 10 power 15 range. And radio, AM, FM radio, they use this range transmission. Television signal transit 10 power 8 range. And microwave for the mostly for the mobile phone communication, they use this range. Terrestrial microwave is this range. So this is the standard electromagnetic spectrum. If you make a mobile phone, you have to follow this rule. Otherwise, your mobile phone cannot be accepted. Okay? You understand? You have to keep the frequency. But just for understanding, you cannot memorize this. Okay? So the high-level summary is that traditional cellular phone technology, mobile phone technology, mostly range from 700 million.
Hello. BIOS. That's how I pronounce your name. BIOS. What's up, BIOS? Welcome to the stream, BIOS. Or is it BlogOS? BlogOS. Wait, is that? Oh, it's blog. I thought it was like B-I-O. It's blog OS. What's up, blog? Welcome to the stream.
With the new mid-spectrum allocation up to 6 GHz and the millimeter wave form allocation with 24 GHz. So So the millimeter waveform with 24 gigahertz mobile phone band is called 5G. You know 5G mobile phone. So 5G mobile phone gives the frequency bigger than 24 gigahertz for transmission. 5G has mobile phone 5G, and you can see 60 also available. 60 more frequency than this one. 60 mobile network. 5G. 5G is the frequency, more frequency. So the mobile phone transmission or cellular phone connection gives a millimeter wave which is greater than 24 gigahertz band. That is the 5G mobile network. So if your mobile phone can support more than 24 gigahertz frequency for transmission of the system, that means your phone is under 5G network. 5G, okay? That means the hardware inside the phone should support this frequency. You understand? 5G. Now we have 6G, more powerful than this one. 6G, okay? 6G. But this book says 5G. A network link is a physical medium carrying signal in the form of electromagnetic waves. So what is a network link? So all the cables which connect network, there is a physical medium and they transmit via what signal? Electromagnetic radiation. Okay. So the data, binary data converted into electromagnetic form. Why? Because electromagnetic radiation is too powerful. Data can reach long distance without any problem. Okay. But here, what we do, inside the electromagnetic wave, that our real data is the binary signal 1 and 0. So we will see that means the binary data is encoded in the signal before it's transmitted. A network link is a physical medium carrying signal in the form of electromagnetic waves. So what is a network? With the new mid-spectrum allocation of 6 GHz and the millimeter waveform allocation with the 24 GHz. So the millimeter waveform with 24 GHz mobile phone band is called 5G. You know 5G mobile phone. So 5G mobile phone gives the frequency bigger than 24 GHz for transmission. 5G has mobile phone 5G, and you can see 6G also available. 60 more frequency than this one. 60 mobile network. Okay? 5G. 5G is a frequency, more frequency. So the mobile phone transmission or cellular phone connection gives a millimeter wave which is greater than 24 GHz band. That is the 5G mobile network. So if your mobile phone can support more than 24 GHz frequency for transmission of the signal, that means your phone is under 5G network. 5G, okay? That means the hardware inside the phone should support this frequency. You understand? 5G. Now we have 6G, more powerful than this one. 6G, okay? 6G. But this book says 5G. A network link is a physical medium carrying signal in the form of electromagnetic waves. So what is a network link? So all the cables which connect network, there is a physical medium and they transmit via what signal? Electromagnetic radiation. Okay. So the data, binary data converted into electromagnetic form. Why? Because electromagnetic radiation is too powerful. Data can reach long distance without any problem. Okay. But here, what we do, inside the electromagnetic wave, that our real data is the binary signal 1 and 0. So we will see that means the binary data is encoded in the signal before it's transmitted in the form of electromagnetic wave. So here the binary data, you can see the binary data from a transmitter or from a sender encoded into a signal. What signal? Signal. Binary data encoded into a signal before its transmission in the form of an electromagnetic wave. So here we don't focus electromagnetic wave, but we are going to focus how the binary data is encoded. Okay or not? Okay? Yeah. Before transmitting the binary data, it encoded and converted into electromagnetic radiation and sent. The receiving side from the electromagnetic radiation, it extracts the encoded data and decode it, convert it into binary. Okay? Anyway, we are going to see the data, binary data transmission in the form of a signal. What is a signal? Signal means encoded binary data transmitted in the form of electromagnetic radiation is a signal. Signal. Okay? Signal. So there are many types of network connections are here. Customers interact with internet through wireless network, Wi-Fi, or you can have access network, that's mainly, by your internet service provider. Yeah. So there are many services are here. DLS, digital subscribe link. So they use copper cable in your phone. GFAS, copper cable, but PON is an optical cable and speed is very high. Okay. Digital subscribe link is an old technology, but right now all the companies they connect internet to our home through the telephone cable. they use models. GFAST is a copper cable-based technology, mostly for apartment building, and passive optical network is an optical connection, mostly used for home and business cable. So this is the DLS architecture. You see, just understanding. Okay, what is a modem? Modulator, demodulator is a computer hardware device that converts data from digital format into a format suitable for analog transmission medium, such as telephone. Or cable-based. Digital subscribe link is a old Wi-Fi, or you can have access network. So there are many types of network connections are here. Customers interact with internet through wireless network, Wi-Fi, or you can have access network. That's my name. By the internet service provider. Yeah. So there are many services are here. DLS, digital subscribe link. So they use copper cable in your home. GFAST, copper cable, but PON is an optical cable and speed is very high. Okay. Digital subscribe link is an old technology, but right now all the companies they connect internet to our home through the telephone cable. They use model. GFAST is a copper cable-based technology, mostly for apartment building, and passive optical network is an optical connection, mostly used for home and business cable. So this is the DLS architecture. You see, just understanding. Okay, what is a modem? Modulator, demodulator is a computer hardware device that converts data from digital format into a format suitable for analog transmission medium, such as telephone or radio. Okay, so this is the internet service provider. They connect network to your home. This is the customer. So in your home, what is your home? You have a telephone connection. So telephone connection, they can connect internet connection. So from the telephone connection, you can use for internet application, and also you can use for telephone application. So this is called the speaker. Okay? Yeah, I think the home. Yeah, you can see this is the AS connection, the cable. So you can use your phone, iPhone, and also you can use the router. This is the router for Wi-Fi. You understand? Okay? Yeah. But this part is the company, internet service provider company or through company or AS company, whatever company. But this is the cable to your home, your apartment here or whatever. Okay? So similarly, the same thing. You have telephone jack and you have modem, router, and you get internet cable connection or Wi-Fi. What is Wi-Fi? You can see an antenna. Okay? Phone line cable. So this is the phone connection, phone line jacket. So this is called DSL port. So if you call some company for internet connection, they will provide this connection to your home because you have a landline. If you have no landline, they will use Wi-Fi from the direct Wi-Fi, or they can use telephone connection. Okay? It is easy to connect telephone line for the internet connection. So most of the home apartment they use telephone line for internet connection. Okay or not? Okay. Now, see, we need to know the main issues. How to transmit the data. Number one issue, how to encode. What is that? Yeah. First issue, the data. This is the data generated by a computer, network computer. How to transmit this data in the form of encode. So encode the data, then convert the electromagnetic radiation, send to the receiver side. So here we are going to see what are the encoding techniques. Okay. Data encoding. Okay or not? Okay? Yeah. Let us take data encoding. You have any question? So this slide has a lot of pictures, and many pictures are taken from the third-party website for making you understand. Okay. Yeah. Data encoding. Okay. Data encoding. You have any question? So all the information are taken from the book. We take some information from outside the source. I put the web link. You can check it. How can a link transmit binary data from the sender down to the receiver node? It's not possible without encoding. So the answer is the network signal propagates our physical link in the form of encoded form. So sending node encode the binary data into signals. It's what encoded binary data and then sent via physically as an electromagnetic wave. But we don't get electromagnetic wave now. We are telling how to convert a binary data into encoded form. Okay? How to encode a binary data. Okay or not? Okay. Similar, this is the sending node. Receiving node, what happened? Decodes the signal back to the original binary data. Decode. Okay? Encode, decode. Okay? That means in our tablet, mobile phone, computer, everywhere, encoding and decoding facility inside. Another is inside. So in practice, binary signals might correspond to different voltage. See, binary signal means we know, 1 0. Okay? 2 voltage. 1 0. 1 means voltage. 0 means no voltage. No voltage. 1 means 5. 0 means below 5, maybe 2 voltage. Anyway, in practice, binary signal might correspond to 2 different voltage on a copper based link. So in a copper cable, it is a voltage. What about optical link? Optical link binary signal is power level. High power, low power, high power, low power. Okay? In optical cable. What about radio transmission? It is amplitude. Okay? Yeah. So amplitude means radio transmission. What is radio transmission? Wi-Fi. Okay? In Wi-Fi, it is an amplitude. So binary data can be different. Environment, different link. What about optical link? Optical link binary signal is power level. High power, low power, high power, low power. Okay? In optical cable. What about radio transmission? It is amplitude. Okay? Yeah. So amplitude means radio transmission. What is radio transmission? Wi-Fi. Okay? In Wi-Fi, it is an amplitude. So binary data can be different environment, different link, different form. In copper cable, it is a voltage form. In fiber optic cable, it is a power form, and in Wi-Fi, it is an amplitude form.
ครับเอาผักรวมมิตรราดข้าวครับเอาไก่ใส่ไส้กรอกได้ด้วยได้ไหมได้เดี๋ยวเอาใส่ไส้กรอกด้วยใส่กรอกนะครับใส่ไส้กรอกประกอบรวมไก่ใส่ไส้กรอกด้วยแต่ว่าลองไส้กรอกอย่างเดียวเอาไก่แล้วก็ไส้กรอกโอเคเดี๋ยวมากินนะครับครับขอบคุณครับ
A network adapter is a piece of hardware essential to all network that connect node to a link. So we need a hardware network adapter. Okay. We are going to see data encoding. Okay, data encoding. So here we are going to see different method of data encoding, and most probably the questions next one there. Okay, data encoding. Okay, now. Okay. The first type of data encoding is called non-referent to pseudo encoding. Non-referent to pseudo encoding. NR sub. Just a simple one. Okay. Non-referent to pseudo encoding. So the network adapter contains a signal component that encodes bits in the signal, and the sending node and the receiving node decode the signal back to bits. So here you can see the figure 2, 3 showing how the encode decode is possible. figure 2, 3. You see, this is a sending computer, sending node, there is an adapter. It is the one perform encoding decoding. So, first encode, send the encode and send to the receiver. Okay, in the bits. Bits are converted to the signal, encoder. So, there is an encoder here, it encodes the signal. And the receiving side, receiver decode, encoding, decoding. Okay, now. Okay. Signal travel between, this is the idea. The sending node encode the bits and convert the signal and send to the receiver. In the receiver side, the signal is decoded and extract the original.
There were some glitches. Was there? Hello? Hello? Oh, MC is live. Still doing this thing.
Yes.
Oh, he's programming for him.
I don't even know what you're doing. What is that?
Control P or Control N.
Yeah.
It's
Wait,
just-
Control P. I have that set to open files.
No, in insert mode.
Oh, in insert mode.
So in insert mode, Control P, Control N lets you select these things.
What? It does?
What do you use?
I don't.
And then
It's ChatGPT or
It's-
something.
when it highlights, normally for me when it highlights, here I'll just open it in Vim.
Or do
test.
user bin so it's
So test, yes. So
hot take. I like this color scheme better.
so if I write XP and complete, I get a specify 2,
So
and
that-
it's like in the document.
I don't get it.
So then I escape and it's there.
I don't get it. Can you answer this for me? So if like Vim can just do this. So like, what did I sell 30 plugins for? I'm a little confused now.
Okay. Now we are going to see the simplest encoding data form is called no returning to 0. Now, the problem of encoding bits on the signal is to map the data value 1 onto the high signal, 0 to the low signal. Here, in no return 0, 1 means high, low means 0. Okay. So this type of bit map is used by an encoding scheme called non-return to 0 encoding. Figure 2.4 shows non-return 0 encoded signal. It's very simple. Nothing, you don't need to do anything, just put the signal, that's all. Okay. So this is a non-return 0. If the bit is 0, it is concerned low voltage. If the bit is 1, high voltage. So this high voltage, low voltage, high voltage, low voltage is called non-return 0 encoding. Okay, now. Okay. Yeah. Same thing. If you by looking the bit 0 is low, 1 means high, low. Okay. So this type of voltage variation. If it's a copper cable, it's a voltage. If it's a Wi-Fi, it's a amplitude. If it's a fiber optic cable, it is in the form of power. Okay. 0 means low, 1 means high. Okay, no. Same. But this type of data transmission encoding has problem. You see, too many 1 and 2. Zero. So how the receiver identify this too many 1, too many 0? Okay. So there is a problem with the non-return 0 encoding as a problem. The first problem with the non-return 0 encoding is that a sequence of several consecutive 1 means the signal is high. Okay. In a long period, see, long period the signal is high, long period. Okay. Similarly, several consecutive 0 means signal is 0 for a long time. Here, not a 0. Signal is 0 for a long time. Okay. Yeah. So what happened? In decoding side, what is decoding? The receiver side, the receiver calculates the average power of the receiver signal. This power average is called baseline. So in this case, the receiver side, it will calculate the power, how many 1, how many 0. So we don't know the equation to calculate power, anyway just say power. It will calculate the average power is called baseline. So the receiver used baseline to distinguish between low and high signal. So what happened? The decoding section, it calculates the power of average power of the signal is called baseline. Based on the baseline, the receiver.
Hello, Data Dev, what's up? I'm going to have lunch in 5 minutes, I think. So, but anyway, welcome to the stream. What you working on these days? I haven't seen you on Stragger's stream whatsoever. Are you been doing your job? Been learning programming, or what is it? Are you making $1 million startup company? Is that what it is? Are you making $1 million startup company and hiding it from the Twitch noobs? I think microphone is something wrong. No. Yeah, it's alright. It's fine. Yeah.
To distinguish between low and high signal. So what happened? The decoding section, it calculates the power of average power of the signal is called baseline. Based on the baseline, the receiver distinguish which is low signal, which is high signal. So a long string of 0 or 1 can cause drift in the baseline called baseline wandering. So too many 1, too many 0, it may confuse. So it is very difficult for a receiver to decode properly. So in this case, too many 1, too many 0 is has a problem. See, the signal is coming very fast, 1, 0, 1, 0, but too many 1, too many 0, then the receiver unable to identify properly. So this is called baseline wandering problem. Okay, baseline wandering problem. Normally, whenever the signal is lower than baseline, the receiver conclude it as 0, otherwise 1. So there are a lot of complexity in non-linear 0 encoding. One of the problem is baseline wandering problem or drift in the baseline. So the receiver unable to identify a long string of 0 or long string of 1. Okay. So second problem here,